Section 2.3, trigonometric identities. And our first subsection, basic trigonometric identities. So this section, first of all, I think is a ton of fun. I think it feels a lot like puzzles and it can be quite enjoyable if you let it. An identity is an equation that has been proven to be true, or that we assume to be true as a foundation of mathematics. 1 is equal to 1. 3 is equal to 1 plus 2. They're simple, they're identities. We have these reciprocal identities. We haven't really talked about them as being reciprocal identities, but it's just the soulmate relationship. That sine and cosecant are the reciprocals of one another. Cosine and secant are the reciprocals of one another. Tangent and cotangent are the reciprocals of one another. We talk a lot about them being the flipsy-flu of each other, right? You just flip the fraction over. But I want to be clear that flipping the fraction over is the same thing as doing 1 over that fraction. So for instance, if I were to say that sine of x was equal to a over b, and I know cosecant is 1 over sine of x, so cosecant is equal to 1 over a over b, right? 1 over sine. If I were to try to clear out the fraction by multiplying by b on the numerator and the denominator here, this would simplify to b over a. So this notation, 1 over that number, is the same thing as the flipsy-flu of that fraction. So those are the reciprocal identities. Just flip over the fraction. Quotient identities, that tangent is sine over cosine, and cotangent by the reciprocal identity is cosine over sine. Those are the quotient identities because you are taking a quotient. You are dividing two things. We have talked about sine squared plus cosine squared equals 1, and we are about to talk about it a whole lot more. This is the most important identity in all of trigonometry. In this section, what we're going to be doing is looking at, I'll just kind of scroll a little forward. We're going to be looking at identities and trying to prove that this is true. This is true. Why? How should I trust that that's true? Where would you start? How do I know that this is true? This is a weird statement. Our goal is going to be taking something like this, starting at one end, and then getting to the other end to prove that one chain of equations, right? One chain of equations can get you from the start to the end. That will be our goal here. We're going to use these identities as those steps. So you're going to want to know what this identity looks like in different ways. And we can rearrange this guy, right? I could subtract cosine squared off on both sides, right? Minus cosine squared x. And if I did that, I would have that sine squared x is equal to 1 minus cosine squared x. Just going to move that. Oops, not that though. So sine squared x is equal to 1 minus cosine squared x. I also changed my colors. My colors on here a little bit to make the difference between colors show up more. I hope this isn't too bright. I might need to pause and change colors. You can also subtract sine squared on both sides to solve for cosine squared. So sine squared is equal to 1 minus cosine squared. Cosine squared is 1 minus sine squared. You want to know these. You want to be able to start recognizing these. These are really important. When you see 1 minus cosine squared, your brain should think sine squared. Same thing with this guy down here. And when you see sine squared plus cosine squared, your brain should say 1. All right, so there's that. Now, here's the thing. There are 3 listed on this page, right? 3 Pythagorean identities listed on this page. By the way, if you're curious about why is it a Pythagorean identity, doesn't Pythagorean's theorem have to do with right triangles? And you would be correct. However, the unit circle, right? We defined each of these points on the unit circle using a right triangle, right? We said that the unit circle's equation was x squared plus y squared equals 1, right? This is just Pythagorean's theorem, a squared plus b squared equals c, where c is the radius of the unit circle. But we said, oh, well, x is cosine and y is sine, and bam, that's where that comes from. So that's why that's a Pythagorean identity, even though it doesn't look like a triangle thing, it is. But there's two others listed here, and they're actually exactly this one. They're the exact same thing. So what you can do with this equation, cosine squared plus cosine squared equals one of two things. Duplicate this, pull this guy down here. All right. I could divide both sides by sine squared. Well, no, let's do cosine squared first. Cosine squared. And if you divide the one side by it, you're dividing everything. Okay, I'm dividing everything by cosine squared. Now, sine squared divided by cosine squared, that's the same thing as sine x divided by cosine x, all being squared because it's squared on top and bottom. Those cosines cancel to 1, plus 1. And then you have the 1 over cosine x quantity squared. You know what I'm doing right now? I'm proving an identity to you. I'm proving an identity to you. I've actually taught this so many times, and I've never taken a moment while doing this to say, I'm proving an identity right now. But I'll say this to you, dear listener. I am proving an identity right here, right now. Not even part of a problem. Anyway, sine divided by cosine is tangent. So this is just tangent squared x plus 1 is equal to 1 over cosine is secant. So this is secant squared x. And hey, what do you know? Wham, bam, thank you, ma'am. That is this guy right here. Obviously, it looks different because it says secant squared first, but it's the same equation. So that's one thing you can do. You can take and divide both sides by cosine squared and get this whole brand new identity derived from the original Pythagorean identity. Or you can divide both sides by sine squared and end up with a similar result here. Sine squared divided by sine squared, those cancel to 1. Cosine divided by sine, for similar reasons as above, this will be cotan squared x, because cosine over sine by the quotient identity is cotan squared. And 1 over sine squared is sine soulmate cosecant squared. And again, wham, bam, thank you, ma'am. We got this guy here and right over here. These are the three main ways these identities are written. They're typically written in this way. However, there are 3 rearrangements of each of these for a total of 9 different ways you can write these Pythagorean identities. So because there's 3 terms, right? 1, 2, 3, you can solve for each of the terms. This first one is solved for 1, the next one is solved for sine squared, the next one is solved for cosine squared. You can do that same thing for this secant squared equals 1 plus tangent squared. You can solve for 1, so you could do secant squared x minus tangent squared x equals to 1. And then you could solve for tangent squared by subtracting 1 on both sides. So tangent squared x is equal to secant squared x minus 1. Finally, for this last one, we could subtract cotan squared on both sides and get cosecant squared x minus cotangent squared x is equal to 1. And we could also subtract 1 on both sides to get cotan squared x is equal to cosecant squared x minus 1. So those are the 9 different ways that you can write the Pythagorean identities. Here's what's going on. My brain automatically can deal with these ones here. My brain knows these, thinks about these, and recognizes them immediately. These ones here, I don't recognize immediately, and I have to derive in my head when I use them oftentimes, unless I've been using them repeatedly in that particular week. Every semester, I just kind of re-derive it for myself. And I think that that's most useful, being able to start here and then derive the remaining 8 of these. It's not super useful to take a bunch of brain space memorizing just knowing how to get there should you need them. It's also important to recognize kind of these pairs. Like if I see secant squares and tangent squares together, there might be an identity. If I see a cosecant and a cotangent squared together, those might be an identity. And same with sine and cosine squared. So these are the identities we're going to be working with, and we're going to, in the next video, work first on simplifying. I think we'll do 2 simplifying videos, and then we'll talk about proving some identities. I'll see you in that video. Bye.